SwayamPrabha. Digital India. Educated India.
Hello. Today in the last lecture we discussed a way to solve Euler-Lagrange equations. They are formidable even for the Brachistochrone problem, the very basic problem calculus of variations. If you do not know more, you can formulate differential equation, but you cannot solve. So, people have developed techniques to solve. When the integrand of the functional, which is an integral, if that has some special forms, there are ways to solve. We discussed those special forms. One of them is called the first integral of Euler-Lagrange equations. Then we discussed two more things, and first let me write what we just discussed, that we have some special forms. Let me get the pen. We had the special form of the integrand to be dependent only on x and y, that turned out to be trivial, and then we took integrand where it is a function of y and y prime, and f as a function of x and y prime, and then we had where integrand was of the form f of x y into square root of 1 plus y prime square. Okay. This and this turn out to be rather straightforward, and these two lead to what is called the first integral of the Euler-Lagrange equation. Okay. Then that was the first thing we discussed. Then we discussed two more things. One is change of variables, and the other is parametric form. Okay. In change of variables, x and y were changed to, so you have y of x that becomes v of u. Okay. That is, x takes the role of u, y takes the role of v. In parametric form, we introduce another variable, let us call it t, x t and y t. If you notice that the form of Euler-Lagrange equations remains invariant, that is, it does not change. When you change x y to u v, form remains the same, meaning that when you convert to u v, we would write dou f, it would have changed, the form would have changed, let me call it f hat or something, dou f by dou u minus d by du of dou f by dou v, sorry, dou f by dou v it will be, not u. Okay, that would have been where dou f by dou v and dou d by du of dou f hat by dou v prime. So, the form of the Euler-Lagrange equation does not change when you do this change of variable. Similarly, parametric form also. Parametric form, what is y prime here? Y prime will become dy by dt, what we call y dot, by dx by dt. So, it becomes y dot by x dot. Okay. So, that is what we discussed now. Now, when you are doing this change of variables and putting into parametric form, there is a deeper result called Noether's integral. Okay. So, when we have this invariance of the Euler-Lagrange equation that we just talked about, there is a more general theorem which is named after a woman mathematician by name M.E. Noether, who was a contemporary of Einstein and a lot of other great people of that time. Okay. It is related to the first integral that we have discussed today. Okay. It is related to the first integral that we have discussed. And first integral we already saw when we looked at one example that it gave the conservation of energy. We took the mass spring model with the Hamilton's principle where we extremized the action integral using calculus of variations, we got conservation of energy out of that. In general, this Noether's theorem also leads to conserved quantities. We will do an example today. As I said, it is named after a lady mathematician who was a German, Emmy Noether, okay, a great mathematician. And for this Noether's theorem, a person of the stature of Einstein praised Emmy Noether for this theorem's penetrating thinking. So, we will have to spend time on this theorem, go slowly to understand what this says. Okay. It is widely used in mathematical physics, where you have this change of variables that you do to simplify things, then Emmy Noether's theorem comes to the rescue. It is widely used in mathematical physics. When you say you know calculus of variations, first thing people ask you, what are Euler-Lagrange equations? You tell them. Fundamental lemma of calculus of variation, tell them. Next thing they ask, do you know Noether's theorem? If you say you know it, then they will believe that you know calculus of variations well. Okay. Now, let us discuss that theorem. Okay. It is about invariance of Euler-Lagrange equations under transformations. Let us say that we have the variables x and y, okay, x and y. We change them to other set of variables denoted, earlier we said u and v, now it is x hat and y hat. Okay. When you are changing from x y to x hat and y hat, then you have like these two expressions, you know, phi and psi, that relate x hat with x y and y prime and y hat with x y and y prime. That we are changing, we are expressing x hat and y hat in terms of x y. We are changing variables, and this is what is the transformation, going from x y y prime to x hat y hat, and you can do other way also. Okay. So, if you know that, then the original problem which is shown here can be transformed to this problem. Okay. So, f is a function of x y dy by dx. Now, it becomes x hat y hat dy hat by dx hat. Limits also is x1 to x2, because that is the integration variable. Now, that is x hat. So, the limits also change. Okay. And in fact, the expression itself will also change, should also be f hat. The integrand will have a different form. It is the same expression, substitute everything, it will have a different form. Okay. We say that if j is equal to j hat, okay, f may be different, but you have different variables, different limits, and all the things that have changed when you transformed that to that. Okay. If j equal to j hat, we say that the functional is invariant under the transformation shown above. That is the first invariance. That is, we have changed from x and y appearing in j. J was dependent on x and y, we have integrated everything, it is a number, and we have j hat which is done in terms of x hat y hat. If this is true, we say that the functional is invariant, it is not changing its value under this transformation. Okay. That is what we consider first. Okay. Now, what this Noether's theorem says is that, now consider the same x hat y hat that we discussed in the last slide. Now, also a parameter that is introduced, then it becomes a one parameter transformation. Okay. We have parameter alpha. Okay. So, basically what it is saying is that x hat is expressed in terms of x y y prime alpha, it would also be y double prime and so forth, but as we have been doing, we always take the simpler case, that is, it depends on the first derivative. If it is second derivative, third derivative, you can work it out, we can work out Noether's theorem once we understand this. So, we are taking only up to y prime, introduce this parameter in the transformation. Okay. We will see what is this alpha, if you wonder why are we introducing, why are we using it here. In our example we take a case where we have a coordinate system, we rotate the coordinate system, right. We have done mechanics or some structural design problem using one coordinate system. If that coordinate system is rotated, that could be the theta, that will be the equivalent of this alpha. So, as we change the coordinate system, do our dynamics change or mechanics change or structural optimal profile will change? It does not, is what this Noether theorem says, or rather it says how it would change. Okay. What remains constant if we do that. Okay. Now, if you take that one parameter alpha here, then the j or j hat are equal, you see, that is what we said. Then that functional is invariant under the transformation. Okay. Then we have this f. Now, we will have this, I should say f hat, I think I am not writing, but when you write it, this form of this expression depends on x hat, y hat and dy hat by dx hat will be different from this thing here. Okay. Now, if it is under if this function is invariant because j and j hat are equal, then what Noether's theorem says is this result. Okay. We have to look at it carefully. What is it saying? We have two things, phi and psi, it is using both in this theorem here. Okay. In this statement here, it says that f y prime, f sub y prime, that is dou f by dou y prime multiplied by dou psi by dou alpha. Alpha is a parameter, it could be rotating coordinate system, that could be theta. The psi is an expression over here, right. We are taking dou psi by dou alpha and then substituting alpha equal to 0, alpha goes away. Okay. And then we have f minus y prime by f y prime times dou phi by dou alpha, where alpha again is equal to 0, that is constant, is like a first integral. That is what we said. Noether's theorem is related to first integrals that we discussed in the just previous lecture. Okay. Now, we also see that first integral does appear what we had taken. Okay. But only thing is we have some additional things, you know, this first term is additional and what multiplies dou phi by dou alpha equal to 0. That is a theorem, we are not proving it here, just understand, and when we take up an example you will see how it is useful, especially derive some conserved quantities that are there embedded into the dynamic system that you are taking or any problem that you are under consideration. Again, we are only taking the case up to y prime, one can extend it to y double prime also, there will be more terms coming here. Okay. Just like in the first integral Lagrange equation, more terms get added when you take more derivatives. But what the theorem is saying is that when a functional is invariant under a particular transformation that is given to you, then this thing is this particular thing is true, okay, where this one parameter transformation, right. What if you have many functions? That is what we normally do, we extend multiple derivatives, we are not doing yet. What if you have multiple functions y1, y2, y3 up to yn, and then y1 prime, y2 prime up to yn prime, still single alpha, one parameter. Then basically what changes in Noether's theorem is this summation. So, whatever we said is constant, now we have to do that for all functions that are there 1 to n, still a single equation. Okay. You have to sum over all things, that is coupling. So, you have many functions, then this is true. Okay. That is just an extension of this theorem for multiple functions. Okay. Again you see this has to be done alpha equal to 0 both psi and phi, where psi and phi are defined like that for each of these functions 1, 2, 3 up to n. Again we should see that j should be equal to j hat, that is the functional should be invariant under the transformation. Now, let us apply to a problem to understand this one parameter transformation using which we have defined this Noether's theorem. Okay. Consider a system with n particles, a mechanics problem, n particles with position coordinates xi, yi and zi as a function of time. Okay. That means there are n particles moving in 3 dimensions. So, each particle has its position vector denoted with x, let us say first particle is x1t, y1t, z1t, second particle x2t, y2t, z2t, and so forth. We have n particles, we have 3n functions, all of which are functions of time. Okay. Kinetic energy of such a system is easy to write, each particle half mv square, that is why we have in 3 dimension x I dot square, y I dot square, z I dot square, that is a total kinetic energy, and potential energy will be a function of x1 y1 z1 and x2 y2 z2, x3 y3 z3 up to x1 y1 xn yn zn. Okay. Now, this is what we call action or Hamiltonian. Okay. So, sometimes it is called action integral or Hamiltonian, people use both of them. This part is what we call Lagrangian, that we use in Lagrangian dynamics, kinetic energy minus potential energy. We have kinetic energy potential energy already written, so we can write this action or Hamiltonian. Now, we consider this one parameter family of transformations, that is why I said the alpha is now the theta. We are rotating, okay, because these things that we have is for a particular coordinate system that you have chosen. What if I change the coordinate system? I am rotating the coordinate system, okay. I am rotating about z axis, looking at this look at this equations, you can tell that z coordinate is not changing, that means that we are rotating the coordinate system about z axis, okay. If my index finger is z axis and x and y are here, okay. Let us see, you can see that I am rotating like this about z axis, right. When I do that, z coordinate does not change, whereas x and y would change, all right. So, if I take this one parameter that we said alpha, that alpha is now theta, okay. If we have this, we would first show that H is invariant under the above transformation, that is we have this action or H Hamiltonian, that should remain the same when you change that. If that is true, then Noether's theorem will be applicable and we will see what will be that one statement that we get, okay. So, we write that down. So, we have x hat, that alpha, now that alpha is theta here, okay. Here xi star is this in terms of theta, yi star is this, this is the transformation you have chosen, there is nothing there, and t equal to t, the time is not changing, that remains the same. So, for the phi there is no transformation in the independent variable. Earlier, just to understand what I mean by t equal to t, there is no transformation, let us go back and look at the statement of Noether's theorem. We had this x hat, okay. Let us look at this thing, x hat was a function of phi. In this case, instead of x we have time, the independent variable, the t equal to t we are not transforming that, whereas y hat equivalent of that here is xi, yi, zi, which are all functions of t, okay, multiple functions. So, this second theorem there we considered multiple functions applicable in our example, okay. Instead of y1, y2, yn we have xi, yi, zi, all of which are functions of time. So, instead of x we have t and then 3 functions, okay. That is how we should look at. So, what we have here are 3 functions xi, where I goes from 1 to infinity, yi, oh not infinity, n, and zi, t and t. So, t takes the role of x on this slide and these are y1, y2, y3, all of which are functions of x, okay. So, having understood that, now we are explicitly writing t star, xi star, yi star, zi star, we are just taking different variables like average quantities here, x bar, y bar, z bar that we have, okay. If you take this, now what we find here is that in fact you should verify that with this transformation. Okay. So, with this type of transformation we are not really going to see a change in our action integral, that you have to verify. Particular transformation you have to work it out and evaluate all of these things here, that this h value does not change, that should be invariant. Okay. Then Noether's theorem is applicable with that. That is a statement when there are I equal to 1 to n, now n is 3 for us. Okay. Because we have taken these functions y1, y2, y3, we have those, and when you write all this, what you get f y I prime will become dou k e by dou x I dot and then y I dot z I dot, and then we have these things that should be evaluated at theta equal to 0. Okay. So, we are basically looking at dou phi by dou alpha, because phi does not have anything. So, that is just 0, that does not occur. We are focusing only on this thing. We have n particles, this I goes from 1 to n, otherwise functions we have are only 3, that is x1 of t, y1 of t, z1 of t. Okay. When you do this, so we are saying that what I just said, dou f by dou theta equal to 0, because t equal to t there is no transformation really there. So, this is 0 and that is why this term will not exist here, only this. Let me just say that this is not really 3, we have particles n particles, but are 3 functions x1 of t, y1 of t and z1 of t, that is what we have, and that is again split here separately. Okay, with y1 one quantity that is x1 and y1 and z1, each of them separately, that is what we have. If you substitute these things using this transformation, we also note that dou x star by dou theta at theta equal to 0 is yi. Then you go back and look at this transformation, take derivative with respect to this dou psi, that is what it is with respect to theta, substitute equal to theta equal to 0, then what you get is this result and this one and then this one. Okay. From there again this is z is not changed, that is why it is 0, phi is the t is not changed, that is why this part is 0, but these two are non-zero. You substitute all of them, what you get here, this term I will color code becomes that, because dou psi 1 by dou theta here that we have comes out to be yi, and then let me use a different color to underline. So, this particular thing becomes that, and these things are 0, because dou psi 3 that we have is like dou z I star by dou theta, that is 0, that will not be there. We get this equal to constant, that is what Noether's theorem says, but now if you look at it, it is mxi dot times yi minus my dot by xi is nothing but p cross r, where p is linear momentum vector. We are talking about particles moving in 3 dimensions. So, linear momentum basically mass times velocity, linear momentum mv, but now v is a vector because it is 3 dimensions. So, that is given by this thing over there. It has components mxi dot, my dot, myi dot, mzi dot for each particle, where I goes from 1 to n, linear momentum vector, and then position vector r. Okay. So, p cross r, that is what we have here, that is what you get when you look at this quantity that is lying there. P cross r summation for all the particles equal to constant is nothing but the principle of conservation of angular momentum. Okay. So, Noether's theorem gives you the conservation angular momentum when you write down the equations, right. We have the Hamilton action integral, that when we extremize it, you get the Euler-Lagrange equations are what we call Lagrangian equations for dynamics of a system. It can be rigid body, elastic system or mixed, whatever system. When you write Euler-Lagrange equations there, the first integrals of motion gives you conservation of energy that we saw earlier, You can get conservation of linear momentum also. Now, we got conservation of angular momentum because we considered a one parameter transformation. So, when you write that action integral, whichever coordinate system you take, its value does not change. That we have not verified, but you should verify by calculating. Since that transformation is invariant, that function is invariant under this transformation, that is a more precise way of saying. The functional is invariant under the one parameter transformation. One parameter here is that rotation about z axis. When you do that, then we work it out, the expression that is there for Noether's theorem says something it will be constant, that something turns out to be summation of the angular momentum follow this momentum vector. It is a P is a linear momentum, P cross R is angular momentum for all the particles 1 to n, this being constant. That statement is what we have recognized as the angular momentum over all the particles that is conserved, and the absence of any external moments and forces acting on it. Okay. So, why is Noether's theorem important? Because it lets us find conserved quantities in any calculus variation problem leading to first integrals. When something is constant, you solve the problem already, the first integral comes out of it. Okay. That is, problem is partly solved. Especially in the context of dynamic systems, you always have second order, there will be acceleration term. If you have x, there will be d square x by dt square. When you have first integral, you reduce it to dx by dt. You know that momentum will have only velocities, angular momentum will also have velocities, because linear momentum vector is p, angular momentum is p cross r. So, that is basically in terms of only velocities, you are not finding the second derivative with respect to time. So, you already solved part of the problem. Okay. And it can be extended to multiple functions, as we saw for x, y, z, n particles, 3n functions we considered this, and it can also be extended to multiple derivatives. Okay. So, that I had said earlier, but now I am emphasizing again that we can work it out or state this Noether's theorem for multiple derivatives also. That is what we have been doing from the beginning. First we take only y prime and then take y double prime, y triple prime and so forth. The same thing can be done here as well. In mechanics, it leads to conservation of linear momentum, conservation of angular momentum, conservation of energy we have already seen. Okay. This previous example showed us how to do this for conservation of angular momentum. Okay. That is why Noether's theorem is important from the viewpoint of mechanics. In the viewpoint of structural optimization, it is hard to say. It is, I have not tried to apply this any time when we did this, because there the coordinate systems and things like that are not that important, but it will be worthwhile to explore that, to see that this Noether's theorem is important for any calculus variation problem where you have some transformation occurring. It is just that people have probably not applied to all problems that exist. Okay. So, to summarize today's lecture, so we considered the first integrals of Lagrange equations for 4 different the various forms. We have 4 special forms we took, and then we use them to simplify Lagrange equations so that we can solve more easily than otherwise. Then we also discuss the change of variables and parametric form that led us to this invariant transformations and this very important theorem of Noether. We have not proved this Noether theorem, but it is a very profound thing. When you have multiple functions, all them coming together to give one equation is important, right. So, normally if you look at Lagrange equations, if there are n functions y1, y2, yn, you would expect to see n equations there. No, this leads to only one equation, because if we took the example of n particles, what we concluded was that angular momentum is conserved for the whole system of n particles. It is not something that is true for only first particle, second particle, third particle, it is not like that. All of them put together, it is constant. That is why this Noether theorem is is a profound theorem. It requires us to think a little bit as to how it works, and if we go through the proof, then it will become more consolidated in your mind. Okay. So, that concludes today's lecture. We will go back and look at a few more things in calculus of variations and application of it especially to the dynamics problems and so forth. Okay. Thank you.